the stress and strain relationship in a high velocity forming. The stress strain curves for aluminium, that is 7075 T6 aluminium and 304 stainless steels are shown here. And the static condition represents the conventional forming, and the dynamic conditions representing the HVF. And in this figure or the curves, we can see that in HVF processes, the strain required to failure are much higher as compared to conventional processes. So that is an indication of a higher ductility in HVF. When a structure is subjected to a rapidly changing load, just like in HVF, the loading has been occurred at the point of application and is carried from that point of application to other parts of the structure by stress waves. And by these stress waves, the energy and momentum propagates by motion of particles of the medium or the material. So this propagation of this load is possible due to the property of medium like elasticity and inertia. Then it is known as elastic stress waves, and these elastic stress waves, the particles always tend to come back to their original positions. So when it is transmitting the load, it will be moving to some other position, then it is coming back to the original position because of the elasticity. That's why it is known as elastic stress waves. And the propagation velocity of such waves depends on density and elasticity of the medium. Thus, these elastic stress waves are classified into different types. The important types are P waves and S waves. And the P waves is otherwise known as longitudinal waves. The P stands for the pressure, so it is also known as pressure wave. And the S wave is S stands for the shear, and that is shear waves, or otherwise the transverse wave. So consider the longitudinal wave. The longitudinal wave, the direction of the movement of the particle is along the direction of the waves, wherein S waves, the direction of movement of the particle is transverse, perpendicular to the direction of propagation of the wave. Here the direction of propagation of the wave is in this direction, and the direction of particle movement is perpendicular to that one. So that is known as shear waves. And in this longitudinal waves, the direction of movement of the particles is along the direction of wave propagation. Another type of wave is surface waves. So in surface waves, it propagates in an elliptical counterclockwise way as shown in this picture. So this elliptical counterclockwise movement results in an up and down. It is a combined up and down motion with a back and forth motion. So it is a combination of longitudinal waves and S waves. And this waves has got a higher intensity on the surface of the material, but if it is propagating inward in the material, that will be decayed exponentially. And the final type is the plastic waves. So the plastic waves, that is deformation, it is happening when the deformation takes place in a ductile materials, when the stress in the material exceeds the elastic limit. So for an under dynamic loading conditions, that is just like in HVF, the resulting wave propagation can be decomposed into elastic and plastic regions. For the derivation of elastic stress wave equation, we are considering an elastic bar of length L and cross-sectional area A, and the material has density rho and modulus of elasticity E, and when it is loaded with a axial impact force, the F of T, at this end, the right end, then the stress wave passes, the element is displaced axially, that is, this is the direction. So the element is displaced axially, changes in length and become stress. And for the purpose of derivation of this elastic stress wave equation, we are considering a small portion that is of length dx from this specimen, and that is shown in this picture. And this length is dx, and the one end or cross section is marked as A, and the other cross section is marked as B. Now on this small element of length dx, we have got two faces, that is A and B. And if we consider the displacement at phase A and phase B is, at phase A displacement is u, and at phase B displacement is u plus dou u by dou x of dx. That is, this portion is the change in displacement of the material, and the stress on phase A is that it is sigma x. Then the phase B, it will be sigma x plus dou sigma x by dou x into dx. Then force acting on phase A is nothing but that area of cross section into the stress of phase A. Similarly, we have got the force on phase B is the area. Area is same, so the area of cross section into the stress acting on that phase. And the acceleration at A and B is given as acceleration at A. The phase A is given as dou square u by dou t square, and same time the acceleration at B is given with this name. Using the basic force equation of F is equal to ma and further simplifications, so we are arriving the wave equation as dou square u by dou t square is equal to E by rho dou square u by dou x square. And here if we consider the motion of the wave or the velocity of the wave is c, capital C represents the motion or the velocity of the wave, then that is given by a relationship. So the c is a function of modulus of velocity of the material and the rho of the material. Then we can connect the c is equal to root of E by rho, and substituting in this equation we can modify the equation, and that equation is known as the elastic longitudinal wave equation, and that is given by dou square u by dou t square is equal to c square dou square u by dou x square. And here we are trying to establish a relationship between the particle velocity, that is the velocity of movement of the particles, and that is given by small v, and the stress. So for that we are using the strain displacement relationship as given as the strain of a point, that is epsilon x is equal to dou u by dou x, and the stress strain relationship is epsilon x is equal to sigma x by E, and the propagation velocity relationship, that is dou x is equal to c into dt, where c we know that this is the propagation velocity of the wave. The propagation velocity of the wave is much higher compared to the particle velocity small v, and this c is, we know that it is actually having a relationship with E and rho as root of c is equal to root of E by rho. So this particle velocity is given as dou u by dou t, that is v is equal to dou u by dou t, and that can be modified as finally it is sigma x by rho c. Initially the dou u by dou t is replaced with epsilon x dou x by dou t using this strain displacement relationship in this equation, and further sigma x is equal to this epsilon x is equal to sigma x by E, and that will be substituted here, and we know that the c is equal to dou x by dou t. So replacing that, applying these two equations here, that is, it will become sigma x c by E, and the E can be replaced with this equation, that is in terms of c and rho. So again that is modified as sigma x c divided by rho c square, and finally we are arriving the equation of B is equal to sigma x divided by rho c. So this is the equation or the relationship between particle velocity v and the stress sigma x. Thanks for watching.